Hi everyone, my name is Hamza Bodor, and I am going to present our work entitled Little Help Makes a Big Difference, Leveraging Active Learning to Improve Unsupervised Time Series Anomaly Detection, that we have submitted to AIOPS at ACSOC conference. It's the fruit of my master's internship at Network and AA Engines at Huawei Paris Research Center, and supervised by Taipei Hoang and Zonghua Zhang. We will start by giving a brief introduction about the problem and its description, and then present our solution to this problem and its experimental setting, and finish by showing the different results and conclusions that we have achieved. In our days, it's known that IT systems are becoming more and more complex because they contain multiple pieces of hardware and software, and there are different dependencies and core interaction between these system components, which make it very important to ensure the functionality of every component. That's why IT firms keep track of different metrics or key performances indicators to assess the health status of networks and services. As the components of the system are increasing continuously, it goes the same for the quantity of the key performance indicators to keep track of, which make it very tough and complex for human operators to do so. Hence the need for a real-time automated solution that can detect anomalies in the system and alert potential failures in real time. This allows to be timely informed of abnormalities and potential faults in the system, prevent the spread of failures to the other components, and ensure a quick correction of the problem. And most importantly, it prevents companies from losing business or customers that interact directly or indirectly with the system. That's why we need to solve the problem of KPI anomaly detection. But first, what's a KPI? A KPI refers to a set of quantifiable measurements used to monitor the performances of a system or a machine. The CPU or memory usage over time is basically a KPI. Mathematically, it's defined as a sequence indexed by time, such that each element of the sequence is among RD. D is equal to 1 for univariate time series, and it is greater than 2 for multivariate time series. The problem of anomaly detection on time series data consists of predicting a sequence Y of the same length of the input X, such that for every observation XY, it outputs 1 if it is an anomalous observation and 0 otherwise. This figure here presents an example of annotated KPI. We can see that there are different types of anomalous behaviors. It can be a spike, it can be a dip, or it can be a complete change of the behavior of the time series. The problem of anomaly detection in time series data presents different challenges. First, there is a trade-off between labeling costs and performances. This is because it's commonly recognized that supervised anomaly detectors perform better than unsupervised ones, but they require labeled data, which is usually difficult to obtain in real-world scenarios. That's why a lot of solutions in the literatures are unsupervised. Also, these models require a lot of parameter adjustment to produce good results. This becomes very challenging as the number of parameters increase, particularly of unsupervised learning results where there aren't labels to give idea about the performances of a set parameters. Furthermore, in a real-world scenario, limited resources are assigned for a system monitoring. This requires anomaly detector to be as lightweight as possible. Typically, a very deep neural network, regardless of its performances, might be very difficult to deploy in production. Also, efficiency is very important in anomaly detectors because we want it to trigger alarms of failures as soon as possible, which requires the model to be as fast as possible. Finally, system metrics may suffer from concept drift due to the change of behavior and routine. Trained models should be able to adapt to such new concepts. To address this, we propose an active learning based anomaly detection model that has mainly three steps. The first steps consist of using a fully unsupervised anomaly detector. For our case, it will be isolation forest model, and use the anomaly scoring of this model to query just most important observation up to an available budget to a domain expert, and use the label feedback from this domain expert to have a labeled and unlabeled data pool. And then we will use this pool to build a semi-supervised anomaly detector that will be more accurate and more aligned with the feedback of the expert. And this loop here can continue until we reach satisfactory results. Our solution solves the different challenges raised previously. In fact, thanks to the active learning paradigm, our approach minimizes the operator's efforts by labeling only a small fraction of the data, and yet conserving comparable results to fully supervised methods, as we will see in the results part. The approach solves the parameterization issue as it can start with the basic model, default parameterization for example, as we will see, and use the feedback of the analyst to update the model to its best parameterization possible. Concerning resources and limitations and efficiency, our solution is based on the isolation forest model, which is not only one of the latest weighted anomaly detector, but also one of the fastest, both for training and inference. Our solution is also scalable to higher dimension due to the linear complexity of the model. For the online update, the pipeline ensures the capability of the model to update and ensures its accuracy, thanks to the continuous and periodic feedback from experts. Now we will give more details about one of the most important steps of our solution pipeline, which is the query strategy. It consists of choosing only a small set of most important observations from all the training datasets. To do so, we propose three query strategies. The first one consists of choosing the most anomaly score according to the model. The second one is close to the decision boundary strategy, which consists of choosing points that are around the decision boundary of the model. Finally, we also explore combining these two strategies by using half of the budget for the first one and the other half for the other one. Another important step in the pipeline is to update the model. It consists of transforming the feedback that we got from the domain expert into an adjustment to the model that will make it more aligned with this feedback and hopefully more accurate. We did this using three possibilities. The first possibility is the tree weights update, which adjusts the contribution or weight of isolation forest trees so that if a tree turns out to be more accurate in its anomaly scoring, it will have more impact in the scoring function. The second possibility is the offset updates model strategy. That's because isolation forest has a critical hyperparameter called contamination ratio. It indicates the proportion of outliers in the dataset and is used to determine the threshold on the scores of the samples. In practice, this ratio is usually guessed based on application context. We propose to learn this offset instead of guessing it. And finally, we propose a combination of the two aforementioned strategy by applying tree weights and offsets in sequence. This figure here illustrates the impact of the above stated model strategies on the score distribution and offset of an isolation forest model. At the beginning, the score distribution of the nominal and anomalous points produced by the unsupervised isolation forest model have a large overlap, and the offset value is not properly set to well separate this distribution. By updating the weights of the isolation forest, these two distributions are pushed further away from each other, causing anomalous and nominal point samples to have higher and lower scores respectively. It should be noted that updating the weights of isolation forest has no impact on the offset value of the isolation forest model, and we still have here some points that are um, false negatives. This offset value is further adjusted so that it can be better separate the two score distribution, and consequently, the adjusted isolation forest model can better distinguish anomalous and points from nominal points. Concerning the experimental setting, we start by mapping the time series sequence into a feature space so that it becomes easier to distinguish anomalous points from normal ones. These features are from different domains, temporal, statistical, and spectral. Also, features extracted in an online fashion, which means that at time t, we only have access to the past values, which is exactly the same setting in real world scenarios. We give a signal of size w of the past to a feature extractor. We extract some features from this signal, and then we will be concentrating ourselves to residual based features, which means that from these features we will extract the current value to obtain the final set of features that will represent the current observation. To evaluate the performances of the model, we will be using two benchmark datasets. The first one is AIOPS. It's released by AIOPS Data Composition. It consists of 29 multiple KPIs with anomaly labels collected from various internet companies. It has 2.26 anomaly ratio, and it is sampled using most likely 5 minutes interval. Also, we use an internal data set that we call Huawei. It is a set of 8 KPIs obtained from different telecom core network elements. It has less anomaly ratio, almost 1%, and it has the same frequency or sampling interval, which is 5 minutes. Finally, we will use the same protocol evaluation used in other time series anomaly detection works in the literature. It consists of basically giving the model the capability to raise the alerts within a tolerated delay. That's because in practice, any model that triggers an alert as quickly enough, it is considered as right. For our experiments, we will use a delay of 7 to be comparable to other state-of-the-art methods. Before presenting the results of our solution, we want to start by benchmarking the different state-of-the-art results alongside with two types of baseline that we built. The first baseline is the isolation forest and is an extreme case that uses 0% of labeled data, and the random forest model that is also an extreme case, but this time uses 100% of the data. We can see that first that the supervised learning method performed better than unsupervised ones, which proves a previous challenge raised previously. Also, we can see that the baselines we built performed better than the state-of-the-art methods, either in supervised or unsupervised settings. This proves the strength of the set of features that we have chosen and their discriminative capability. Finally, we can see that for three different parameterization of the isolation forest, we have obtained completely different results. This proves that an unsupervised learning model might be good in theory, but may lead to very hard results if it is ill-parameterized. That's why we will prove that our solution solves this issue by starting with this weakest model uh, as a baseline for our active learning solution. And when we do this, we obtain the following results. One can see that our solution performs better than similar solutions in the literature, mainly active anomaly detection via ensembles, which is a similar solution that starts from isolation forest, but updates the nodes of the weight of the nodes instead of the weight of the trees as we are proposing. Also, we can see that our solution requires less query budget and is much more faster than the other one. Finally, one can remark that our solution reached the performances of the fully supervised model that has been trained with the same features, which proves that our pipeline can make the isolation forest performs very comparable to fully supervised one. As conclusions, while our solution even starting with a weak unsupervised model and by using only a small fraction of the labeled points can increase its performances by more than 50%. Furthermore, it achieves results that are very comparable to fully supervised results. Also, it has been proven that our solution is in general 10 times faster and more accurate than other more complex solutions. Finally, the results prove the importance of the proposed model offset update strategy, as the best performances are always reached when using or evolving this strategy. Thank you for your attention, and I will be happy to answer any questions that you have.